All right, let's look at some graphs, and in particular some discontinuities of graphs, and describe them involving limits. Now, in the first drawing, we've got a line that has a hole in it, and you can see we've got the hole on the line at 3, 2. So there's an ordered pair where there's the hole. Okay, now the problem with the hole is it's rather deceiving. It looks like it has area. And if we drew that to scale, you would not notice that. But that hole looks at this point like it has area. Okay, so we've got this linear function that has a hole in it at one spot. It's redefined above the hole at the position 3, 3. Okay, so the first question we've got to fill in here is, what happens as we approach 3 from the left, f of x? Now, in this case, we're using limit notation, so we're saying the limit of f of x as x approaches 3 from the left. Now, 3 from the left looks like 3 raised to the negative sign. So 3 from the left. So we've got the graph to look at. So we're asking, what happens to y as we approach 3 from the left? Now, we're to the left of 3, so we're approaching 3 from the left of it, and as we move closer and closer to 3, the function behaves like 2. Now realize that's where the open circle is. However, the limit talks about the behavior of the function. It does not pinpoint at that integer value. It talks about behavior. We're talking about descriptions here. Now, the second question we've got here is, what happens as we approach 3 from the right? And notation-wise, 3 from the right looks like 3 raised to the positive power. So what happens to the function? What does the output of f of x look like as we approach 3 from the right? So now in this case, we're to the right of 3. And as we move closer and closer to 3, we can see again there is that open circle there, but as we discussed, that's already deceiving. Okay, it looks like it has area. It really doesn't have area. So as we approach 3 from the right, the function is behaving like 2. Okay, so far we've looked at the value 3. We've got a left side limit at 3. That's 2. That's a one-sided limit. We've also got the right side limit at 3. That's also 2. Again, that's a one-sided limit. Okay, so the next question we've got is, well, what happens to the function, the limit of f of x, as x approaches 3? Now this one doesn't have a little plus or a little minus like in the first two parts. This just has the integer value 3. Now what that's referring to then is a double side limit. Now the only way a double side limit can exist at a real number value, 3 here is a real number value, the only way a double side limit can equal a real number value is that if we have the left side limit equal a value and the right side limit equal a value. Now if these two values are the same, then the double side limit is automatically that value. So our double side limit here is 2. So we've got a left side limit of 2 at 3, a right side limit of 2 at 3, and a double side limit then is also 2. Now the next part is kind of a review question. It says, well, what is the function at 3? How is the function defined at 3? Now, this function does have a dot, a closed circle above that open circle of 3, 2. And again, graphically speaking, we've got the point 3, 3. So the function is defined at 3 when we plug in 3 here. So the output is 3. Okay, the last two questions we've got to answer are what is called end behavior. We want to know what happens to this function as x approaches negative infinity. Also, what happens to this function as x approaches positive infinity. Now, if you were in an Algebra 2 class, again, this would be talking about end behavior. Okay, end behavior is something you can discuss as far as asymptotes, okay, as far as horizontal asymptotes or oblique or any other slant asymptotes, if you will, with rational functions. Now in this case we've got a linear function. Again, a linear function other than we've got this discontinuity here when x equals 3. That was discussed over here in parts A through D of this question. So what is the end behavior as x approaches negative infinity? So if we're on our graph, we can see that this arrow is pointing to the left, it is going down, okay, and what that tells us is that this function f of x diverges to negative infinity, okay, which again does not exist, but for notation we will write negative infinity here to show that we have a limit that does not exist. So as x approaches negative infinity, f of x goes to negative infinity as well. And again, limit speak, that diverges. It is a divergent function as x goes to negative infinity. Okay, similarly, we want end behavior way to the right. What happens way to the right? As we plug in larger and larger values for x, what does our output look like? Okay, and so here, as we move to the right, we can see that the arrow also moves in an upward fashion. The function keeps increasing. It's unbounded to the right. As x approaches positive infinity, then we would write positive infinity here to show that that limit does not exist. And as we move to the right, the function keeps moving upward and goes to the right as well and goes in an upward fashion. So the output would be positive infinity as well. Okay, so the first 4 parts of this question, we're looking specifically at a real number value at 3. We had a left side limit, right side limit, double side limit, and the function. The last 2 parts we're dealing with the end behavior of that function. And in this case, we do have a discontinuity for this function, and this discontinuity would be categorized as a removable discontinuity. A removable discontinuity is a discontinuity such that the double side limit exists. Our double side limit is 2 here, so that would tell us that because we have this 2 here and we know that we've got the double side limit there, we know that that's a removable discontinuity, and in this case it is discontinuous. However, the function is defined elsewhere. Okay, let's look at another graph. This function g of x, we've got again something interesting happening, and this is an interesting part, is when x equals 3. So we're going to go through and answer the same type of questions. We've got the left side limit for g of x at 3, the right side limit for g of x at 3, and then the double side limit of g of x at 3. Okay, as well as the function at 3. So left side limit at 3. Again, as x approaches 3 from the left, it looks like we're raising it to the negative sign here. Okay, so as x approaches 3 from the left, we're on this piece of the graph, this piecewise function. So we're here and we're approaching it. And again, there is an open circle at that -1 output spot. But again, the function, the limit descriptor does not care about that open circle. So we would write -1 here. Okay, so we've got a left side limit at 3 of -1. Okay, right side limit, we're to the right of 3. Now we're up on this piece of this function, g of x. And up at this piece, as we approach 3 from the right, the function is behaving like 3. So we've got a left side limit of -1 and a right side limit of 3. Okay, well, just as before, the only way a double side limit at a real number value can exist is we have to have a left side limit equal a real number value, a right side limit equal a real number value, and those real numbers have to equal one another. In this case, they do not. So this double side limit does not exist. I'll abbreviate that with a D and E. And any time in calculus I write a DNE, which stands for does not exist, I like to explain that to the best of my ability. So in this case, I've got a left side limit of -1, and I'm going to write that does not equal 3. Now what that tells the reader, as far as a descriptor is concerned, that -1 does not equal 3, is that we do have a left side limit that exists, which is -1, and a right side limit that exists, which is 3. And in this case, we would call that a jump discontinuity. A jump. We've got a gap there, And if you were physically walking from one of the lines to the other, you'd have to jump. We've got a jump discontinuity. Now lastly, at 3, we want to know what is the output. And in this case, we've got a closed circle at 1. So G of 3 equals 1. Okay, and since A, B, C, and D are all different, we know we are discontinuous at that value, and in this case, that value was 3. Okay, so what about the end behavior of this function? As x goes to negative infinity, I'm down on this piece, on this horizontal line, this constant. Now the limit of a constant is a constant. And to the left of 3, this piecewise function is behaving like -1. So our answer here is -1. The limit of g of x as x approaches negative infinity equals -1. Okay, what about the right end behavior as x approaches positive infinity? Okay, so now the output, again, to the right of 3, because we're approaching positive infinity, that output's up at 3. And again, just like to negative infinity, we're dealing with a constant piece, a constant function to the right of 3. Okay, so in this case, we have a jump discontinuity at 3. And again, we've got a left side limit and a right side limit that are both real number values. However, they do not match, which tells us we have what's called a jump discontinuity there. And that automatically tells us then our double side limit at that value does not exist. This function g had output of 1 when x equaled 3. That was this random closed circle up here, and that was at the ordered pair 3, 1. Lastly, we discussed end behavior. As x went to negative infinity, we were at -1. As x went to positive infinity, we were at 3 up on this piece. Okay, the last graph I have up here has, again, a discontinuity. This discontinuity is up at 4. Now, in this case, we would call that position 4 a vertical asymptote. And in this case, that would be where a function is undefined, okay? And if we were talking about it in the calculus speak, we would be talking about a discontinuity here. And again, this is an asymptote. And I wrote the equation of the asymptote up there, if you can see it, at x equals 4. Okay, so let's ask some limit questions at the value 4. So we've got a left side limit at 4. What's the limit of f of x as x approaches 4 from the left? Okay, what's the function doing just to the left of 4? What does the output look like? So in this case, we'd be on this piece of the graph to the left of this vertical asymptote, and we can see that that function is rising, it's increasing without bound, and that would be a does not exist, and we would say it's going to positive infinity. Okay, what about to the right of 4? As x approaches 4 from the right, what is the function doing? What does the output look like there? Okay, so as we approach 4 from the right, we're to the right of this x equals 4 asymptote, and again, we're increasing without bound, and we go to positive infinity. Ran out of room there on this graph. Positive infinity, okay? And again, that does not exist, but we explain our behavior with that positive infinity. Okay, well, the last thing we've got is, what about the double side limit at 4? We've got the limit of f of x as x approaches 4. Well, so far we've done a left side limit, we've done a right side limit, and we can see that both of these do not exist. But again, we will write positive infinity here to explain that behavior that we know they're going upward. So because both of these are positive infinity, I'm going to write a positive infinity here. Now, because everything is positive infinity at this asymptote, we've got the same behavior to the right and the left of this vertical asymptote. We could categorize it as a even vertical asymptote here, because we've got the behavior going in the same direction. That's an even vertical asymptote. Now, the next question is, what about the function at 4? Now, there aren't any closed circles for the graph at 4. We've got that vertical asymptote at x equals 4. So that would tell us then that the function is undefined. Now, undefined is good language for functions, where we would say for a limit it does not exist. So functions undefined, a limit does not exist. Okay, last thing we need here is the end behavior of this function f. So, as x approaches negative infinity, what does the output look like? Now, if we're interpreting this graph in the same manner, we can see that this green line approaches the horizontal. The function f of x approaches the horizontal. It looks like it has a horizontal asymptote at the value 0. So, as we approach negative infinity, that function is behaving like 0. Okay, what about the end behavior way to the right? Okay, so as we go to the right, x approaches positive infinity, and as we move to the right, it looks like this function is bending up towards -1, and it looks like it's plateauing there. And again, if we interpret this graph the same way, I would say that the end behavior way to the right is -1, and in this case it would have a horizontal asymptote in that direction. So in this case we've got the vertical asymptote here. It's an even vertical asymptote because we've got the same behavior to the right and the left. In this case, both going to positive infinity, which tells us our double side limit went to positive infinity. In this case, our function at 4 is undefined, good language for functions. And we lastly had the end behavior, 0 to the left, -1 to the right. So we discussed 3 different types of discontinuities here. We had a removable discontinuity with the hole here. Double side limit is a real number value. We've got a jump discontinuity. We've got a left side limit that's not the same as a right side limit. And then lastly, we had an even vertical asymptote where the limits at that real number value for x, they went to positive infinity for all of them. Okay.